So today we are continuing our conversation using the non-random to liquid model, the NRTL model. In the last video, we derived the activity coefficient and we understood that the activity coefficient could be used to modify our Raoult's law. That looks something like this. And what we had done with the Raoult's law previously is we had derived equations and calculated the dew pressure, the bubble pressure, dew temperature, and bubble temperature, which are all very useful things to know when dealing with vapor-liquid equilibrium. So a bit of a refresher, and this time we're going to be doing it using our modified Raoult's law. First up, let's look at our bubble pressure. Bubble pressure. Now, as a bit of a reminder, if we have a bubble pressure, that means we have a constant temperature and we are adjusting the pressure until the first bubble of vapor forms within our system. And we want to find the pressure of our system when that happens. So let's start off with our modified Raoult's law. Equal to YIP. We understand by Dalton's law that if we multiply the overall pressure by its component the vapor mole fractions, then what we have essentially is the sum of the partial pressures. So I'm going to take a summation on both sides here. If we take the summation of yi, we have 1. So essentially what we have is the sum of our liquid mole fraction times our activity coefficients times our pure component vapor saturation pressure is equal to our bubble pressure. So that's easy enough. We can actually just go into Python and start coding that out. Bring my keyboard. So what I have here is our system, our compositions, our temperature, so everything really that we need to start coding this out. So I'm going to define a new function called our bubble P, and this time it's going to be our NRTL model. We also have inputs of our composition and our temperature. The first thing we want to do is we had learned how to pull the gamma, our activity coefficients, using our properties library. So we'll go p.nrtl gamma at our given composition and temperature. I might have to run all of this. I'll just keep coding in the meantime. So we have our gamma now, and we understand that our total pressure, our bubble pressure, actually no, let's start with our partial pressure. So I'll use our PI, and this is representative of our YI times P, that's our partial pressure. And so we're going to have an X times our gamma times our vapor pressure at our given temperature. So I'm just going to make sure that we pulled our G properly. I think I have to do within this. And then making sure that we get our proper values. That is what we got in the last video. So yes, we are good on that front. So we have our partial pressures now, and in order to find our total pressure, we're just going to take the sum of our partial pressures. So that's easy enough. Now we want to find, so I'll return this. What we want to find is of course, we want to find our bubble pressure, but we also want to find the composition of that first bubble of vapor that we have. And if we go back into our whiteboard, if we wanted to find this, essentially what we'll end up doing is we'll be dividing our left-hand side here, so all of this, which is actually equal to our partial pressures over our total pressure. So Pi over P. So let's just run this. Let's see if it gives us good values. So Z is our compositions, T is our temperature. Let's run that. And it looks like we have our bubble pressure is equal to around 22,000, 23,000 pascals. And we have compositions of our first bubble of vapor. So the next step would naturally be getting our bubble temperature. Let's just stick with the bubble train. We'll go on to the dew points later. So for our bubble temperature, we have the same setup. So xi, gamma I, pi set. And we remember that saturation vapor pressure has a temperature dependence. And that's important because this temperature is actually what defines our bubble temperature. Now, when we have a bubble temperature, we are saying that we have an isobaric system, and we are slowly adjusting the temperature until the first bubble of vapor forms within our completely liquid phase. So, to summarize, basically what we are trying to say, Pi set T minus, so remember we do our summation here, cross this out, that's 0. Or sorry, that's not 0, that's 1 because of the sum of our fractions. So the sum of our left-hand side variables minus our overall pressure has to equal 0. And the temperature that satisfies this requirement is going to be our bubble temperature. Now, as a bit of a tangent, when we go into Python, we're going to have to give an initial guess for our root solver to actually do its trick. However, our root solver very heavily depends on a very good initial guess. Well, what's something that we know has a lot of data to back it up? What other than our Clausius-Clapeyron equation? So 1 over... Well, let's just look it up, shall we? So our Clausius-Clapeyron relates 2 temperatures and 2 pressures. Clausius-Clapeyron equation. 1 over T2. Oh, so P2 over P1, T2 minus T1. But if you multiply this into that, it can be T1 minus T2. So, okay. Or divide that, and then that would have to be P2 minus P1 over P2, so T2 minus T1. Okay, that works. So 1 over T2 minus 1 over T1. So we already know what our P1 and T1 is. That's going to be our normal boiling point, and our atmospheric pressure, normal boiling point. We have our P1, P2, or P1, T1 pair. And then we're going to be adjusting our pressure to find our due temperature. And solving for that temperature will give us our initial guess. So this is actually a method we can use to find our initial temperature guess. So let's just try and get this T2 isolated. So R natural log P1 over P2 divided by our heat of vaporization plus our 1 over T1 all to the minus 1 power is going to be equal to our T2. Did I do that right? I think so. So yeah. This is all stuff that we can use to get to our initial temperature guess. So I'm going to start by defining a new function. I'm going to call this my test. Now my T estimate. And I'm going to give it inputs of pressure as well as compositions, and you'll see why in just a moment. So what I'm going to return is basically I want to wait. Well, let's just start here. So R times natural log P1 over P2. P1 is going to be our atmospheric. So R times, I should probably define R, right? R equals 8.314. And this is joules per mole Kelvin. I also added in a pressure in between cuts here, and that'll be used in this input. So we have an R times MP log our, so 101,325, that's going to be in pascals, divided by our pressure, our P2 of interest. All of that is going to be over our heat of vaporization. So all of this over P dot H HVAC, right, at our given temperature. So that'll be at our yeah, that'll be at our given temperature. And then we're gonna add T1, so plus 1 over T1, which is gonna be our normal boiling point. So P dot TBN is gonna be our normal boiling point. And then all of this will be over 1. So let's just do a test here. So T estimated at, let's say, our system is going to be at atmospheric, so 101,325, and then we'll give it our Z. There we go. So we have normal boiling point of water is 373. Normal boiling point of isopropanol seems to be just a little bit lower, which makes sense. It's more volatile than water is, so it's going to start evaporating at a lower temperature. And essentially now what we're going to do is we are going to multiply each of these by X, and we're going to take the sum of these boiling points. So now when we do that, it gives us a weighted boiling point average for our mixture, which it falls between 355 and 373, get around 362. So since it's a 60-40 mixture, we're weighted more heavily on the isopropanol side than we are weighted on the water side. So this gives us a nice little function that allows us to do an initial temperature estimate, a good temperature estimate, for when we go through and do our bubble temperature calculation. So now let's start writing out our bubble T function. So I'm going to bubble T NRTL, and we're going to have to give it inputs of composition and our pressure. And what we're going to be doing is we're going to be using sp.optimize root scalar, and this will give us, this is basically an iterative method that allows us to calculate a value that will make our function in question equal to 0 by adjusting our temperature values. So what we have to do is first we're going to define an unnamed function, so we're going to throw in a lambda with inputs of t, and we're going to actually call back to our bubble P NRTL with inputs of x and t minus our overall pressure, because that's what we're going to be wanting to set to 0. So for this, we just want our first value, because remember we're returning both pressure and our composition. We just want to return the pressure. And basically what we're saying is, okay, we need to set this function equal to 0 by adjusting our t parameter. So that's essentially what this piece is doing, and if we subtract our overall pressure, we should get 0 for that, and the temperature that sets that equal to 0 is our bubble temperature. So we need to make an initial guess, and our initial guess is going to be our temperature estimation at our given pressure and composition. We're going to set a method. We're going to use the Newton method. Newton method. And we just want the root of this. So let's just see. Let's just take a look at this right now. So let's just return that. And so we'll go bubble T NRTL, and we're going to give it inputs of X and P. If we do that, or sorry, Z and P, there we go. We get 353.46, and this is essentially saying that this is the temperature of our mixture that gives us our bubble pressure. In short, this is our bubble temperature. But we also want to be able to return our compositions of that first bubble of vapor. So I'm just going to save this. So T is going to be equal to that. And we also need to define our gamma. So let me just grab that from up here. So there we go. We have our gamma. And now in order to return our vapor phase, we have to divide this entire thing by our total pressure. So we're going to do that. So we're going to return, of course, we want to return our bubble temperature. And we're also going to return our Z times, or sorry, our X times our gamma times our P dot P vap at the given temperature. And then all that over P. I think I just throw that like that. So now when we do our bubble temperature calculation, we get our bubble temperature, and we also get the compositions for that first bubble of vapor in our 100% liquid system. So we're going to approach the dew pressure and dew temperature in a bit of a different way than we had done it in a prior video. We're going to start off the same though. So we're going to define a new function, and this is the NRTL, and we're still going to want to give it a Y, our vapor composition, and we're still going to want to give it a temperature. Now I'm also going to go off and I'm going to define a new function, and I'm going to call it EQ, and it's going to have input of some vector. Now, if I gave it some vector of inputs, I would expect the first however many of those inputs to be compositions. And then that very last one is going to be the temperature, or sorry, the pressure at which these compositions pop up. So I'll say X is going to be equal to everything in our vector except the very last term, and then my P is going to be that very last term, right? Now, there are a couple things here that I want to zero out. So let's just start up here, why not? So at the dew point, that is so for pressure, of course, we have an isothermal system. So we're not really focused on the saturated vapor pressure. What we are focused on, however, is the fact that we have a first drop of liquid in an all vapor phase. So what ends up happening is that we end up changing this pressure, and then at some pressure, we produce the first droplet of liquid within our system. So now, in order to get into that, we would take we would have to set these sides equal to each other because of this temperature, which we are setting for the saturated vapor pressure, is constant. So this is all constant, which means that we are adjusting this side to be 0. And so we can go ahead and we can say, so our x times our gamma, which we would need to define our gamma. I'll copy that here. I guess that is fine. So our x times our gamma times our p dot p vat of temperature equals our y times p. And so basically this minus that is going to be our target function. Now, the other target function that we have is if we have the sum of our x's and subtracted it by 1, these should also be 0. So we can return both of these, and these targets at our given temperature should have to equal 0. So I'm going to make a quick little change. I'm just going to take this and substitute that in for our G here, and we're going to give it back its inputs that we originally had it with, and I think that should wrap that up pretty nicely. I'll take this and put it into an array. And now let's go back to our original function, our DUP. So what I have imported up here are actually our dew pressure and dew temperatures based off of our original Raoult's law before the activity coefficient. And what we can end up doing is we can use this for good initial guesses for when we go on and use our root solver to give us our dew pressure. So what I'll do here is I'm going to take, we're going to unpack the, we're going to unpack our outputs here. So it actually goes in order P and then X, and that's going to be equal to our DUP with our inputs of Y and T. As you can see, that follows that nomenclature that we have up here. And then what we're going to end up doing is we're going to go through and we're going to have our optimize function. So SP the optimize dot I'm going to make sure that this concatenates into a row, so that'll be a row concatenation of that. I think that might be best, just to make sure that we're going to run into any errors later on. So we're going to do this to our EQ function, and we're going to be using our X and P. So I'm going to do another row concatenation, and then throw our X and P into that, and then we just want the root of that. Make sure this all follows. I think I need these around here. And then we'll store this into a result. And basically, we're going to do the same thing we did up here. So we're going to say that our X is everything in our result except the last, and the very last thing that we have is going to be our pressure. So it's going to be our very last value there, and we're going to return our bubble pressure and we're going to return our vapor composition. So x times p dot NRTL gamma. Not sure why it's done that. Inputs of x and t all over our total pressure. So now let's take a look at our due pressure function. Put in our inputs. I think I just need to initiate this. So there are a few things that need to be changed up here. First and foremost, we're going to be using just the root function, not the root scalar function. I also don't think we need that, because that'll automatically grab our root. And we need to specify that we are taking out the x array. So now if I do that, we have our due pressure, and we seem to have very low values for our x's, and that's because I think we just need to pull out the x. And there we go. We have our pressure, we have our liquid compositions, and actually our due temperature is going to follow a very similar sequence. So what I'm going to do is I'm just going to copy and paste this over. It's going to be our due temperature with inputs of our compositions and pressure. We're going to return our temperature back from our array. That'll be all right. That'll be all right. That'll be all right. We're going to use our due temperature function that also has inputs of pressure. So we're going to pull out our temperature and our mole fraction, use that as inputs for our roots, pull out our temperature here, and return it. And if everything has gone according to plan, there we go. We have our due temperature and we have our compositions as well. Now, if we compare this and our due pressure, so let me just do that. So we're still gonna have our composition as Z, but now we're gonna use this as our input, and that brings back out our atmospheric pressure, and we have the same mole fraction. So that just ensures that everything that we have done so far does work. So now the last thing that we might want to do here is go ahead and plot this out and give us a VLE diagram using our non-ideal conditions. Well, in a previous video, I did something very similar where we were using our Raoult's law, so ideal conditions, to create this. So I'm just gonna use this as a template. So I'm gonna take this and I'll explain what all of this does in just a moment. And then we want to make this figure. Right? Now here's the thing with this bunch of code that we have here. So first we are creating an array of x's from 0 to 1, 21 evenly spaced, so it'll give us 20 individual values between 0 and 1. We're setting our pressure, which is a little redundant because we've already done that, so I'm just going to get rid of that. We have an empty array for our temperatures, an empty array for our vapor compositions. And we're basically saying for x, which is our counter, in our column concatenated x1s and then 1 minus x1 is going to be our x2. For each of those, we want to run our bubble T calculation, except now in this case, we're going to be running the NRTL version of it, which we have just calculated, and it's going to be using this function up here. So what we're going to be creating is a TXY diagram. Essentially, then what's going to end up happening is that we're going to append each temperature value to our T's array and append each Y value to our Y1's array. And our T's and Y1s will be reinstigated with our T's and Y1s and we're going to be row concatenating those. So it gives us that list of values that we'll be plotting up against our temperature. Or sorry, up against our x's at a given pressure. So what we are changing here are our temperatures, our x composition, and our y composition, and that gives us our TXY diagram. So we have a make subplots here. We have our bubble, we have our dew, and then this one here is just an XY diagram that we have. And so I think the rest of this should be good, except now we have isopropanol and water. Let's run it. Let's see what it gives us. All right. So we see now that this doesn't look nearly as clean as any of these graphs. There's a bit more of an irregularity almost. I'm going to give this more spaces so it looks a bit smoother. And I might actually go ahead and change this so it's a little bit easier to visualize. Right. So we see down here that we have our bubble curve in this blue. We have our dew curve at this in this red. And we see there is an area of vapor liquid equilibrium. They seem to almost touch right about there and then come back out. And that is what's known as an azeotrope. So there are these two zones of vapor liquid equilibrium almost that we have. And we have something similar over here. This is our XY curve. Up against a 45-degree line, there's an area where they intersect. And if we look at that intersection point, it's at around 0.67. This is also around that 0.67, so they correlate with each other. So this is where our X and our Y's are actually equal to each other. This is where our vapor phase and our liquid phase mole compositions are equal to each other. So I've pulled up from online a diagram of an isopropanol water system, and this is at pressure equals 60 kilopascals, so 60,000 pascals. And the azeotrope kind of lies a little bit lower, I would say. You could take a look at that on our XY diagram. But that's because we're not running the same pressure here. We're at atmospheric here. So let's jack up our pressure a little bit. 60,000 kilopascals. Or 60,000 pascals. Rerun all that stuff. Let it load for a little bit. And it should give us approximately, let's see where these are equal to each other. I'd say right about here. So 0.6 repeating 7, 0.665. So that is about where I think I would say that our other azeotrope lies. So yeah, all in all, good stuff.